So here's kind of a difficult concept in spectroscopy, and it shows its head kind of simply at first in IR, and simply is, I'm not trying to be mean there. So if we were to look at the two signals crudely drawn here, because this is a nice broad peak, fairly intense, we might specify this as an OH, particularly because we're looking at it centered, 33, 3400, right? If we look at the red one, we're just under 3000, kind of sharp, intense peak. We're looking at CHSP3s. Okay? In and of themselves, that's not a big deal, okay? Because if we put that together in a spectrum, it would just look like a normal spectrum. So our combination, purple and then this, right? And we'd be okay with it. But the extra kind of complication that could potentially come out is that if you went through and looked at the OH, there's a secondary feature here, is that if I have that OH near a carbonyl, the carbonyl affects the chemistry of the OH, causing it to shift to lower frequencies. Okay, so if that's the case, if it did actually shift to a lower frequency, then we aren't going to be at 3500 when we're centered. Okay? What happens is that that same signal for an OH would show probably, and now if we did a little shift here, our new center here is about 3000. Okay? The problem with that is that if I then put these two, if both of these signals were present in my compound and in my spectra, I would see first the signal for the OH, and then I'd see the signal for, and again let's draw in that crude or approximate 3000 line, which I'm not doing a very good job of, but where's that 3000? What do I say, somewhere like this. There's our 3000 mark. If we were to go through and now draw in the CHSP3s, well, they're scattered somewhere in there like that. Well, in this case, when you look at that, you're like, oh, well, that's obvious. I can see the blue line and the red line. Mike, that's not a big deal. One's an OH and one's a CHSP3. But remember, the spectra, or the instrument doesn't detect that. What the instrument detects is just, is there an absorption at that particular wavelength? So really what ends up coming out of this is a combination of both of those signals. And the signal we would get would be something that starts nice and broad and then has this bunch of weird jagged stuff and then flatlines back out again. And so what we get is something here, a conglomeration of signals that doesn't really match the CHSP3 and it doesn't really match the OH. Because notice we've got a breadth behind this, it's nice and broad, but then we also have this sharp kind of pointy peak that doesn't make sense for an OH. Okay, so it doesn't really look like an OH. It also doesn't look like the CHSP3 because it's broad. Okay, and the issue is that those two signals are overlapping each other, which then confuses the entire matter. Okay? This same phenomenon will happen in other forms of spectroscopy. And it can make a signal that you might be like, well, that's relatively simple to understand, might make it very, very complicated because there isn't enough differentiation in where the signal appears to differentiate two different pieces of information. Right? And that's what can make IR complicated, and it's also certainly what can make other forms of spectroscopy complicated, which you will see further on down the semester. So if you happen to see a signal, kind of like the one in purple here, that looks like kind of a crossbreed hybrid, okay, of two things, it is quite likely because it is a crossbreed hybrid of two things. Okay? And what we're seeing is a blending of those two. Hopefully that helps to make a little bit more sense of one of the more complex aspects of IR.